My name is John Rath. I'm Director of Operations for NY-GEO. We are absolutely pleased to see you here. I have the pleasure today of handling the CEUs, the credits, as well as introducing the speakers. Can I see a show of hands for people that have pre-registered for credits, CEUs? Okay, what you need to know is at the end, I'm going to be up front here with a sheet that's got your name on it. I need you to sign it. That's all we need. I'll have the pens, and then you're good to go. If you haven't had a chance to pre-register for the credits, there'll be another sheet up here. You'll have to fill out your name and your email and a few other things. But we're trying to make it as speedy as possible, and I'll probably be up in this section. Please, if you have any questions about that, let me know. We're going to get right into this session, and this is the technical design track. We have the title being Means and Methods for Metering Low Temperature Thermal Energy. If that's not what you wanted, you're free to get up and find the one you wanted. Our speaker is Connor Dacquay. Sorry. And he is an international expert. He works in the United States. He works in Canada. He's got over 30,000 tons under his belt. I don't know if you can, how that sounds. 30,000 tons of thermal energy under his belt. And he's going to talk today. He is a certified GeoExchange designer. He is a doctor, a PhD. And what I'm most impressed about is he says he's a problem solver. And don't we need enough problem solvers here? We could use all we can get. Like you folks, you're all problem solvers as well. We've got about a little under an hour, and we're going to leave plenty of time for Q&A. So with that, I'm going to turn it right over to Connor. Thank you, Connor.
Thanks, John. Okay, we have a little time crunch this morning, so we're going to step right into it. So we're first going to talk about hardware, right? BTU meters, thermal energy meters, what are they composed of? And we'll understand that it's pretty straightforward. Standards and regulations, we'll look to Europe, Canada, and the US, what they're doing. Then we'll look at software, right? You have your hardware, but what do you do with that data? How do you collect it? And make value, important decisions from that data. And then geothermal energy as a service. We'll go through a couple of case studies, see what's out there in terms of standalone systems and district systems. So as John alluded to, there's learning objectives. So hopefully if I do a good enough job by the end of the session, we'll learn how to measure a BTU. We'll also understand factory and on-site calibration, and then understand the differences in a connection fee and consumption fee. So a BTU, what is a BTU? Well, if you break it down, it's by definition 1 pound, it's the amount of heat required to raise 1 pound of water by 1 degree Fahrenheit. But if you break it down into an equation, Q, which is your BTUs per hour, then you have your specific heat of your fluid, which is your known fluid properties. And if you know your fluid, then that's fine, but then you have your M here, which is your flow rate. So we need to know that, and then our delta T. So what do we need if we break this down, right? We need our flow rate and our delta T, so temperature sensors and flow meters. For temperature sensors, we could look at a couple different types: thermocouples, resistance temperature detectors, and thermistors. Thermocouples, they work by leveraging the difference between electrical properties and thermal properties of metals. And basically, when you heat up two different metals, there's a differential voltage between the two. And that differential voltage can be correlated to temperature. The benefit of these is that they work over a wide temperature range. They're quite rugged and durable, very low cost, quick response, but they do have a lower accuracy, these thermocouples, and they tend to drift over time. So we're going to talk about calibration in a couple of slides, but that's important to note there. Resistance temperature detectors, or RTDs, you've probably heard of these. Basically what this means when you hear PT100, it's made of platinum, and at 100 ohms, it's 0 degrees Celsius. So there's a direct linear correlation between resistance And basically how that works is as you heat up a metal, the atoms get excited, they're bumping into each other. That traffic jam is resistance. And so if you know the resistance, you can back calculate the temperature. So these are pretty accurate. And we'll get into some problems with small delta T in a bit. I know that's a hot topic as of late. They're linear, right? We talked about this linearity. Repeatable. The downside is they work over a lower temperature range, but that's not really a problem in GEO because we work over a pretty narrow temperature range. Slower response time, fragile, and they do cost more than thermocouples. Thermistors work in the same way in terms of the working principle, but they're made out of different materials. So polymers and ceramics, and they're nonlinear, so their curve between resistance and temperature is nonlinear. So that's our delta T, that's our temperature, right? When we know our delta T, what do we need now? Well, we need our flow rate. And in order to get that, we need a flow meter, and there's several different types of those. There's ultrasonic, Venturi, magnetic, turbine, oscillating jet, and vortex. Sound pretty cool. We're only going to talk about a couple today. And the first one is ultrasonic spool. And the spool part is it's a spool of pipe. And how this works is that there's transducers in that spool that are communicating to one another. And it works by transit time. So the transducers are talking to one another, and the amount of transit time can be correlated to the flow rate. So the faster the transit time, the faster the flow rate. And that's how these things work. There's no pressure drop, so that's good. They're reliable and quite accurate as well. But the downside is, and you'll see this trend with cost related to pipe size for in-pipe solutions, right? Because it scales with the pipe size. A 1/4 inch or 3/4 inch flow meter that's inline is obviously cheaper than a 4-inch. So that is something to consider. And it's obviously also sensitive to the fluid characteristics and pipe condition and installation environment. Ultrasonic clamp-on, same working principle, it's still transit time, but you're clamping those transducers onto the pipe now. And so the problem is that it can be quite finicky because they're communicating to one another. So the transit time is calculated from sending one signal to the other, and you can imagine you have to line these things up pretty accurately on the pipe, but it's non-intrusive, so for a 2-inch application, it's the same cost as a 10-inch application, which is great for retrofits, right? So it's pretty easy to install, it's non-intrusive and low cost for large diameter pipe. However, due to that sensitivity of placement of those transducers, it is lower accuracy. They also require an ultrasonic couplet, which is quite messy, and the pipe condition and installation environment affects the accuracy of the reading and the communication between the two sensors. Venturi flow meters work by leveraging the relationship between flow rate, velocity, and cross-sectional area of a pipe. So we have a known velocity at one point if we know the cross-sectional area. Then we constrict that cross-sectional area, know the new velocity, we can calculate the flow rate. So again, we have no moving parts. It's quite durable, high reliability, and a higher accuracy. However, intrusive, therefore costly. And in this case, there is a pressure drop because you're constricting that pipe. Magnetic flow meters, these work by inducing a magnetic field. And then as the flow runs through that magnetic field, there causes a differential voltage. And that differential voltage can be translated to a flow rate. No moving parts again, pretty reliable and low maintenance and higher accuracy, but the trend here is when it's an in-pipe, it can be more costly because it scales with that pipe size. Last one, before we get into some standards, is turbine flow meters. So turbine flow meters, the working principle is pretty straightforward. As you increase the flow rate, you increase the RPM, rotations per minute, and if you know your RPM, you can back calculate your flow rate. So it's a direct measurement of the flow velocity, pretty simple design, but there is moving parts, there's a pressure drop as well, and then again, intrusive and costly. So we've talked about the temperature sensors, right? That's our delta T. We've talked about our flow meter, our flow rate. That's all a BTU meter is. It's just a combination of temperature sensors and flow meters, right? So nothing too spectacular there. And what governs the standards of these BTU meters or heat meters is EN 1434. And this was created by the European Committee for Standardization. And basically what this does is it ensures the accuracy, reliability, and compatibility of heat metering across Europe. And this was created in 1997, so quite ahead of their game. Measurement Canada is a Government of Canada agency, and their primary mandate is to ensure the integrity and accuracy of measurement in the Canadian marketplace, and they regulate and enforce the accuracy of water, natural gas, electricity, and BTU meters. So they're a little behind the ball here. They implemented EN 1434 in 2019, so pretty recently. So we can look to them to see what they're doing because the US equivalent, NIST, doesn't have a BTU standard right now. There's no heat metering standard for NIST, which is the National Institute of Standards and Technology. So what is Canada doing? Well, as we mentioned, there's a new thermal energy division. They have 20 approved BTU meters that can be used for the legal trade of the commodity BTUs. And basically what happens is if you're a manufacturer and you think you have the latest and greatest BTU meter, you ship this to the lab in Ottawa. They do testing on the BTU meter. They test each subassembly. So the temperature sensor they test, the flow meter they test, and then there's a calculator portion. They test that as well. And they sum the errors. And we'll get into that after a brief Q&A session. But basically, if it's approved, then you can legally trade BTUs. And a thermal energy meter for commercial use must be class 1 or 2, and then residential is 2 or 3. So this is what they look like, right? Nothing too novel here. They're just temperature sensors and flow meters combined with this calculator piece on top of it. So if you go into a building, if you're doing a site tour, you know, and you see one of these things, you can say, hey, you know, Connor showed me one of those. They're nothing too spectacular, just temperature sensors and flow meters. So we like to split these things up into sections to retain engagement. You know, there's a lot of issues these days with notifications and pulling your attention, so we're going to stop for Q&A sessions right now, and then we can jump back into it. So is there any questions?
Connor, let me get the microphone.
Yeah, thanks, John.
Yeah, of the different. Oh, Greg Kamoulis, Con Edison, working on the thermal energy network side. So, of the Canadian approved meters, is there any technology of all the different metering types that you've seen that they are more approved of, or do they approve types of all of them? Can you talk a little bit about that?
That's a great question. Majority of the 20 that I've seen are ultrasonic spool, right? So we'll flip back here. These types of flow meters and RTD temperature sensors. That's the majority that I've seen. However, there are some that are different types of flow meters. That's why I went through a couple of these, just to get, you know, familiar with the technology. You know, it's somewhat boring, but it's good to understand the working principle behind these things.
One more follow-up, and are they approved for billing purposes as well?
Yes. Yeah, go ahead.
Claire Kirk, Eversource. We've been using some PLC BTU meters. In other words, instead of having an actual meter, it's calculated through the PLC.
Okay.
Have you seen that?
I have not. What does PLC stand for?
Oh, like, so the SCADA system or
Oh, I see.
programmable.
Okay.
So instead of having a physical meter, it's just calculated, and you get the same data.
Yeah, that's certainly possible. I'm sure it's the same type of meters. We'll talk about software in a bit.
Yeah,
there's probably
software.
there's a communication layer that's communicating to that BTU meter that's pulling that to the SCADA system.
It's a lot cheaper because BTU meters are pretty costly. So you get to eliminate the physical meter and just have the same data.
So there needs to be sensors.
Right. Oh, yes, so sensors are there, but not a physical BTU meter.
So what are those sensors?
flow, you know, all the ones you mentioned.
So that's a BTU meter. Sure, yeah, but it's just a combination. You can build your own for sure, right? But it's just a combination of delta T and flow.
Thank you. Andrew Wilcox from Undercity Energy in Toronto. Just a couple of comments on some of those metering technologies, less of a question, but the clamp-on ultrasonic meters, I'm not sure that any clamp-on meters are actually approved for billing purposes under Measurement Canada, so that's one thing. Also, I mean, great tools for sort of validation of flow rates or BTU measurement in especially industrial applications. But when if you're trying to measure chilled water, be careful cutting open insulation on chilled water pipes to clamp on a meter, because you can end up rusting the pipe and fouling up the sensors. So pay attention to the conditions of the fluid which you're trying to measure, because interrupting a continuous insulation on something that will condense can cause some real problems later.
Yep, no, good point, Andrew. The ultrasonic clamp-on, as you alluded to, they're not approved by Measurement Canada. However, you know, I think it's a low-cost option for a retrofit, right? If you want to measure the BTUs of an existing GEO system, it's a great option. That way you don't have to crack open pipes and such. So, yeah, we'll do a couple more questions, because I know we do have somewhat of a time crunch. So, yeah, Tim?
Yeah, hey Connor, Tim Ashmore, CDM Smith. Can you talk a little bit about durability of flow meters versus BTU meters?
So it's the same thing, right? Again, a BTU meter is just a composition of flow meters and temperature sensors. So the only thing extra that can degrade is that calculator piece or the temperature sensors. So it'd be the same degradation rate. It just depends what flow meter is in that BTU meter, if that makes sense, right? Because it's just a combination of those things. Yeah, Joe. Here, I got you.
Joe Hitt with DPS. Are you aware of any draft standards in the U.S.? Nothing?
Yeah, I mean, if there's somebody from NIST here, feel free to speak up, but I'm not familiar with anything, no. Yeah, Aaron, last one here.
All right, thank you. Aaron Pike with National Grid in Massachusetts. Curious if there's any size guidelines that generate the best, be it pipe size and flow quantities that give the best readings for some of those ultrasonics?
Yeah, interesting question. The ultrasonic clamp-on or? Yes, both. Yeah, so the ultrasonic clamp-on, the transducers come in different size. So if you have smaller pipe, the transducers are smaller. You know, we'll get into small delta T considerations in a bit, and I know that's a concern of yours, but that, you know, you can have a reasonable delta T on a small pipe too. You just have to match your flow rate with your pipe size, right, and your system capacity. So maybe we'll keep going here, but great questions, and you know that's why it's good to retain this engagement here, because nobody wants to listen to me talk for very long. But we'll keep going here. So, Measurement Canada, as we mentioned before, they measure each subassembly. So they measure the flow meter in the lab, they measure the temperature sensor in the lab, and they measure the calculator. And they sum the errors for each, and then if it's above a threshold, which is based on the measurement equipment and test parameters, but typically around 2 to 4%, then it passes, right? And once it's passed, then again, you can legally trade BTUs with that meter. If we look into other industries, you know, there are some concerns about the accuracy of these BTU meters. If we look at other commodities, natural gas, water, electricity, it's around plus or minus 1.5%, and this is the NIST Handbook 44. So, you know, we're not too far off in terms of these BTU meters being accurate. It's just, and we'll get into the low delta T consideration, but it is comparable, and also in terms of price, you know, it's relatively comparable as well, because you can think of a water meter for a 2-inch pipe versus a 3/4 inch pipe or a 1/4 inch pipe. It's different cost, and these BTU meters are as well. So they scale with the pipe size in terms of the cost. So when you buy Measurement, and we're going to talk about Measurement Canada because this is the most recent approval, and NIST doesn't really have anything. So when you buy a Measurement Canada approved BTU meter, it comes with this factory calibration certificate. And what you'll often find, which is good, that these devices often have a higher accuracy than the minimum acceptable threshold. So that's a good thing. And you can look at the certificate to see what that accuracy is. And that's important because you can have some sort of confidence with this device. But as we alluded to before, there is some concern with temperature drift, temperature sensor drift over time. And it's important to consider on-site recalibration. So ongoing recalibration of your sensors. And what that means is that you measure against a high accuracy control, right, in the field. You ensure stable conditions, and you measure across various temperature ranges or flow, but it's difficult to measure flow in the field against a high accuracy control. And then the frequency is dependent on the application. So how often you do this is dependent on how critical your application is. And what you're left with is an equation that you can offset that sensor to match it to that high accuracy calibration standard. And if we look into other industries, sometimes in geo, we like to think we're a little special. You guys know what I mean. And if we look into other industries, they have to have high accuracy temperature readings, right? Aerospace, hospitals, nuclear power, pharmaceuticals, biotech, these guys need high accuracy temperature readings. So high accuracy temperature readings, that's not necessarily a problem that hasn't been solved. A challenging thing that's been arising in the industry is small delta T, however, because in geo we do have that issue, which isn't quite as common in other industries. So what I mean by delta T or small delta T considerations is, we mentioned before those resistance temperature detectors. Those are the highest accuracy temperature detectors. Let's say those are 0.05 degrees Fahrenheit off, right? And you have a delta T of 1. Well, if you have two temperature sensors that are 0.05 degrees Fahrenheit off, that's an error at 10% at 1 degree delta T. So that's a problem. But with thoughtful pumping strategies, you can avoid that low delta T scenario. So that's one consideration. You could have calibration of the temperature sensors. And then we're kind of jumping ahead here because we're going to talk about energy as a service at the end. But if you lack confidence in your BTU measurement past a certain delta T threshold, what you could do is apply a fixed fee past that threshold, right? So if you get below, 2 degree delta T, you could say, we no longer lack confidence in our BTU meter, we're going to charge you a fixed fee, or something like that. This is just an idea, but again, we thought we'd slip this into the deck because it is a question. So we talked about hardware, right? And it's just temperature sensors and flow meters, nothing too spectacular. But when you buy a BTU meter, and anyone can go buy a BTU meter, but there are local storage limitations. I don't know that SCADA system, how long-term they're monitoring that, but there may be, we're going to jump back, there may be some storage limitations on there if it's not connected to a data rack or a server. So it's important to have some sort of software stack that's communicating with your hardware and storing that data, not only for long-term data collection, but also data organization and analysis, and then graphical interpretation. I don't know about you, but I don't want to stare at raw data all day. I want something to tell me what I do with that data in an intelligent way and how I can make decisions based on that data. So how do we talk to that hardware? And don't worry, we're not going deep on this stuff, but it's important to kind of understand these things when you're reading or talking to folks. You can be somewhat fluent in the control world language because it is a whole can of worms. But BACnet and Modbus are communication protocols. So if you hear that, you can think of communication protocols. MSTP is for BACnet. RTU is for Modbus. That's serial physical communication, which is RS-232 and RS-485. So that's the actual cable for that physical communication. And then if you hear TCP/IP or IP, that's Internet Protocol. And that's Ethernet, which is a physical connection or Wi-Fi, right? So that's how we pull the data from the BTU meter and send it to the server. And what it looks like is something like this, right? So we would have our high accuracy approved BTU meter. You'd have some sort of gateway where you send it either to a remote server or local server. Our preference is to work with a third-party custodian to not only store the data, but perform analysis on it. Specifically somebody who knows GEO as well, so they can make informed decisions or have automated reports that make informed decisions. And what something like that looks like can be this for long-term data trending, right? So we see our typical sine wave of a GEO system, right? Looks pretty familiar. We get up to around 90 in the summertime and down to around 40. This is 3 years of data. So you see 3 sine waves. We have our delta T in our flow on a macro scale. And then we zoom in on the specific day. We have our delta T in our flow. And once we have that, then we can calculate our BTUs, right? Our total BTUs and our peak BTUs in terms of total load and peak load. Once we have that, then we can look over specific time intervals, right? We can look over maybe a week. You want to look at your delta T, your average delta T for the past week, or maybe your total cooling load for the past month, or your peak heating load for the past month, something like that. You can take this a step further, and Ryan Carta is doing a session after the break about ground heat exchanger design. It's my opinion that for every geodesign, the best practice is to build a building energy model, right? To quantify the heating and cooling loads. But the problem with building energy models is you're using something static to design something that's dynamic, that changes over the years. And what I mean by that is your static building energy model is just an assumption of how the building operates. So when the lights are on, how many people are in and out. But that's going to change, right, throughout the year after year of the system. And so if you have your BTU meter that you're pulling data from, you can compare the actual BTUs that ground loop is seeing compared to the building energy model that was used to design the ground loop. And so that can be pretty interesting. And another thing to consider is typical, and in my opinion, best practice is you project out that future ground heat exchanger temperature, right, over 20 years when you're designing the loop, and then maybe you look at it in more granular detail over 1 year. Well, if you're pulling the data from that BTU meter and collecting it every 30 seconds or every so often, you can do that same projection, right? Just like you did when you were designing the loop to make sure that you're sustainable over time. And you could take that a step further and integrate into an auxiliary heating or cooling device to make sure that your ground loop is working as intended and as designed for the life of the system. So that's just some of the things that a smart, intelligent software stack can do for you with a BTU meter. And then also generate automated reports, because again, we don't want to look at raw data. We want to report to make a decision. Billing information summary, if we have BTUs, quite easy to apply dollars per BTU. Summary of the ground heat exchanger performance, and then recommendations for optimized operation. So again, we're going to stop here before we jump into energy as a service to retain that engagement. Yeah, Greg.
Thanks. Are any of the standards in Canada or Europe, do they cover the calibration levels? Is there like a set calibration guidance that we could apply for us?
That's a good question. I don't think so. I think there may be, other corporations or standards that look at calibration of temperature sensors. I don't know off the top of my head what those are, but I'm sure that maybe ASHRAE or other folks.
And the Canadian listing of meters, is that available? Is the Canadian listing of meters available publicly?
If you go to this website, you can look at all of them. Yeah. You have to type that down pretty quick, but I could send you it after. Hello.
Hello, Bob Carver, NYSERDA. I'm really enjoying this presentation. I really appreciate you for putting it together. You touched on one thing that I'm really interested in that comes up a lot, and that's like the frequency and storage of data. And we do a lot of M&B kind of work, and this is a debate we always have about how long, how often. Do any of these standards, are they giving any guidance on storage or frequency of data collection, or are there any established best practices yet in the industry? Thank you.
It's a great question. So EN 1434 is just the hardware stack, right? That's just the hardware piece, I should say. The software stack, I haven't seen any sort of standards on how often you should be collecting data. What I would say, and this is my opinion, it matters on the frequency in which you're concerned about. If you're looking at a ground loop over 20 years, you probably don't need data every 30 seconds. Maybe every hour, maybe even probably every hour, I would say. If you're looking after 20 years worth of information, that's a lot of data to store, which can be quite expensive. AWS or Google would love you, right? But it may not be that practical to store that much information. However, you could. But again, I think the answer to that question would depend on the application and what your end goal is with that data.
Hello, my name is Nkiru from the city of Albany. I just had a question about the third-party provider for software. What kind of companies or kind of things are we talking about there? Are we talking about like sending it to AWS or an IBM or something, or is it a lot smaller entities?
Yeah, great question. So there's a couple folks who will, abstract away that for you. They'll probably work with, a big cloud provider like AWS and store their data on their servers, but there are companies who will take pull the data from the hardware and then store it for you and then analyze it for you. So there's companies, I'm thinking of Hobo Logger sells hardware, and then they also have some sort of software stack where you can look at, just basic temperature and flow. QMC is a Canadian company where they look at, just collecting that basic information as well. But GeoPhys is the only company that I've seen that actually analyzes that data, generates custom reports for you in an automated fashion. You can also work with an engineering firm, right? Engineering firms will sell you their monitoring service. They'd love to do that. I'm sure they would. But it's not really automated. It's just some guy in the back room looking at the data, which is okay, but it could be more costly than working with an automated software stack.
We have a question over here.
Hi, Carl Lozon from Celsius Energy. I think my question probably pertains more to the ultrasonic meters, but is it typical for manufacturers to provide flow guidance for ensuring proper readings from the flow meters? And in your opinion, when you're obviously speccing pipe sizes and things, you're not always going to be dead nuts on the sizing. So for ultrasonic specifically, do you recommend to be more on the turbulent higher side or lower laminar side of the speccing, or is that guidance that you typically see from the manufacturer anyways?
Are you referring to the clamp-on?
It doesn't have to be either the clamp-on or the pipe spool.
And are you referring to the actual laminar flow or turbulent flow of the fluid running through the pipe? Because that kind of depends on the geo design, right? That depends on the pressure drop that you want to see in that system, the circulation pumps that you specified as the engineer for your specific ground loop. Yes. In terms of the flow conditions in which a flow meter works best on, yeah, that'll be in the specs. But whether it's turbulent or laminar flow, that's kind of up to the engineer who designed that system. And it may vary depending on, maybe you have a VFD on that circulation pump, right?
Right.
So it's going to change from maybe transitional to...
Is there trade-offs in the accuracy of the readings based on those flow conditions?
That's a good question. I don't know the answer to that off the top of my head, but feel free to grab me after this and we could find that answer out.
Sure, thanks.
Okay, we're gonna keep going here. We got 20 minutes or John's gonna kick me out of here. So energy as a service for GEO is relatively new. But if we look back in history, the history of water measurement certainly isn't new. And the first recorded use of a water meter, it's a little different. Water's not the same as BTUs from the ground, but it's interesting to look at that the first recorded use of a water meter was in the 1850s, and then the first widespread installation of water meters for billing was in the 19th century in Europe. And at this point, this was the difference between a connection fee and a consumption fee, right? So a connection all-you-can-eat fee, and then a consumption fee. When we look at geothermal energy as a service, that's kind of where we are today, right? And for a standalone system, it's quite common. What a geothermal energy as a service utility will do is they'll approach a condo corporation, and this is very common in Toronto. They'll say, hey, we know the fixed cost of our ground loop. We know reasonable accuracy what our operating costs will be for that ground loop. We're going to charge you a fixed fee in terms of your annual heating and cooling costs. You get certainty as a condo corporation for your heating and cooling costs, and we get a modest ROI. And it seems to work pretty well. 25% of the new condos in Toronto are going GEO, and probably a good handful of those are energy as a service. And so what they do is they have a plate and frame heat exchanger that separates the ground loop from the building loop, and that's their line in the sand, that's their delineation point. And then they sell BTUs to the condo corporation, but it's typically a fixed fee. And so that's great, for a standalone system, but it gets a little bit trickier when you're talking about district systems or multiple heat sources and sinks and multiple buildings. So Whisper Valley took a similar approach to a fixed connection fee, right? So Whisper Valley is a system in Austin, Texas, in the States here, where they have 400 plus homes with Enertech heat pumps currently. That's the best of my knowledge, at least. 300-foot vertical boreholes, 4 separate ambient loops, and cooling towers, which could be seen here, and future phases planned. I spoke with a homeowner in July of 2022, and what this guy told me is he pays around $50 to $60 fixed fee to the geothermal utility, that's EcoSmart. They have an electric utility as well that they pay another, 50 to 70 bucks a month for their electricity usage for lights, any electrical appliances, and then a $20 co-op fee. And the homeowner was pretty happy with this. Compared to relatives, he was paying a lot less in terms of annual heating and cooling costs. So he was a happy customer. And so that fixed connection fee can certainly work, but a little bit more interesting district system, and not to say that Whisper Valley isn't interesting. When I say interesting, I mean more complex rate structure, is the city of Richmond in British Columbia. These guys have 4 vertical fields, 2.2 miles of 20-inch pipe for the supply and return lines. They have 3 backup natural gas boilers, 2 backup cooling towers, 1.9 million square feet of residential gross floor area, and 300,000 square feet of non-residential gross floor area. This is the system, so they have a fire hall, Walmart, condos. And what they did is the city of Richmond has this offshoot company called Lulu Island Energy, very West Coast name, right? And Lulu Island Energy owns and operates this district system. And what they do is they have a connection fee, which is $9.56 per square foot. They have a consumption fee based on the Measurement Canada approved BTU meter for every off-taker, which is 0.7 cents per kBTU, so quite small, very small actually. And then they have this excess demand fee, which is pretty interesting. And how this excess demand fee baseline is developed is a professional engineer in British Columbia, a licensed engineer, will develop a building energy model for every off-taker that wants to join the loop. And that building energy model will set the baseline of the space heating and cooling loads, and maybe also domestic hot water, or if there's other maybe process loads on the system. If the Measurement Canada approved BTU meter measures that they're above 20.5 BTUs per hour per square foot, they're going to charge 62.7 cents per BTU per hour per square foot. So a pretty hefty fine. But what this does is it kind of prevents wasteful consumption. right? And so that's pretty interesting. We think you could take this a step further, and folks are always talking about balance. You got to balance your loop. You got to make sure your heating and cooling loads are balanced. But there's no incentives or alignment between the tenants. Yeah, 1 second, sir. We're almost done. Between the tenants and the stakeholders, right? The tenants don't care whether or not your loops are balanced. Why would they? They're just paying their bill. And so if you had a heating and cooling dynamic billing based on that ground heat exchanger trend, you could look at something like that, right? Because you're pulling in this data, you have the information. And so maybe if you have a heating dominant district loop, you want people to cool. So you could incentivize them to do that. Or if your loop flips to cooling dominant, maybe you rebalance every quarter or every year. But you could change the heating and cooling rates in terms of a consumption fee in a dynamic way that would align both the stakeholders and the tenants, which is kind of an interesting idea and something to consider. So the learning objectives, for those continuing education credits, we have to do these questions to make John happy. So we're going to open it up to the crowd. First question, what are the 2 types of sensors needed to measure BTUs? Temperature sensors and flow meters. What is the difference between factory and on-site calibration? It's kind of in the name. Yeah. So factory calibration occurs from the manufacturer, and on-site calibration occurs on-site. Last one, what is the difference between a connection fee and consumption fee? Yeah, connection fee is a fixed fee for the service connection, and a consumption fee is variable based on usage. So we actually have a little bit of time here, 15 minutes. So we can chat, and if I don't satisfy your questions, feel free to grab me after this. But thank you very much for listening, and this has been great.
Hi, just have one quick question. This is Chris Dolicky, DPS. The connection fee, is that a monthly charge?
I believe it's billed the frequency of monthly, yeah. But I mean, it's rolling, right?
Okay, but it's like a monthly bill. That's the fixed fee.
Monthly,
and then
yeah.
usage.
Well, the fixed fee is monthly as well.
Thank you.
The city of Richmond? Yeah, that's been operational since 2013. You can go see it if you want. In terms of existing buildings being converted to GEO on a district scale? Well, hopefully there'll be lots in New York soon, but yeah. Are you aware of any that exist? I'm not, no. I don't know if that thing works, John. Do you want another? We're out.
No, I've got it.
Just question about why square feet versus cubic feet when you're talking about heating and cooling? It's based on square feet?
That's a very interesting question. I don't know the answer to that. I mean, gross floor area is a common term in the industry, but I mean, volume, that's a pretty interesting question, because if you have vaulted ceilings versus, you're heating up a volume of space. So I don't know the answer to that, but yeah. 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 Maybe that's a hack you could build, Yeah, back there.
Good morning, thank you. I'm Aaron from SUNY. I'm the energy manager for the campus. I got a question about the district concept in Canada. Does that offer support for breakdown? Is it quicker, the response time? I mean, it seems like around here we're waiting a couple of weeks when, we need support, technical support. With these people invested in the actual district, so to speak, does that offer advantage to response time for support?
Yeah, another great question. So Lulu Island Energy, they just kind of own and operate. Stantec is an engineering firm. They design the system. And I'd imagine, I don't know this for sure, but I'd imagine Lulu Island Energy as contractors, like a service contract that goes out to fix, heat pumps and such, and loops. But that's a great question. I don't know if Lulu Island Energy has, technicians on staff with, vans and trucks that go out to site specifically. Yeah. It's a great question. I have the contacts, and I could give you those contacts for this district. One fellow's name is Constantine, and the other is Alan. They're pretty helpful, and they can answer those questions.
While people are thinking of their next question, I did not mention that, and I want to give recognition to your company, GEOptimize, for allowing you to come and talk to us. Any other questions? Okay, while you're still thinking of questions, let me just reiterate that I'll be up on this front table, and I'll have two types of forms. One is for those people that already registered and paid for their CEU credits. All I need is a signature, so bring your glasses because it's kind of small print. Those that would like credits but haven't registered in advance, I've got a separate sheet for unregistered folks, and we'll take care of that in a little while. Okay. So, questions? If not, then Connor, thank you very much. Can I get a round of applause for a great presentation? We're going to continue the CEU track in this room, but if you want to take a break, go out and talk to some exhibitors, use the restrooms. Please be back at 11 o'clock. Thank you.